What's up, you guys? Indie scientist Kenyo here, and we are back reacting to another video from PBS Spacetime. This is What If Gravity is Not a Fundamental Force, Entropic Gravity. Let's get into it.
We're told there are four fundamental forces: strong and weak nuclear forces, electromagnetism, and gravity. Except maybe gravity is actually no more fundamental than, say, the force of a stretched elastic band. Maybe gravity is just an entropic byproduct, an emergent effect of the universe's tendency to disorder. So, if you allow that entropy to hold you in your seat for a bit, I'll tell you all about it.
It's interesting. So I have my little hypothesis. I definitely think gravity is a force. But I like this a lot because I think entropy, this is my hypothesis, entropy is the fourth dimension, time, and gravity is the fifth dimension. And so, let's see how they flow.
Quantize it to unify quantum force. At least it's not in metal forces. It's enormously weaker than the other three, and it's also not a quantum force. At least
About
it's
gravity.
not in general relativity, our best description of gravity. And gravity has steadfastly resisted our century-long effort to quantize it, to unify it with the other fundamental forces. But what if that's because gravity isn't quantum? In fact, what if it's because gravity isn't even fundamental? There are a number of proposals along this line, including the buzzy recent work by Jonathan Oppenheim, but we're going to have to come back to that, because there's an idea that you've been asking us to cover for years now. That's the emergent entropic gravity of Dutch physicist Erik Verlinde, who tells us that it's not some fundamental force or the curvature of spacetime that's keeping you in your chair right now, but rather the rise of entropy on the boundary of the universe. Today, we're going to lay out the basics of Verlinde's
Sounds
entropic
awesome.
gravity as it was published back in 2010. We'll follow up with an episode on the evidence and the criticism and what the idea has to say about dark matter and dark energy. This episode follows directly from our last one, where we explored how space can emerge as an inward projection from its infinitely distant boundary through the holographic principle. A lot of what we talk about today will draw from that episode, so it might not be a bad idea to check it out. But let me recap anyway to emphasize the most important stuff. I'm also going to sprinkle in a bit of math, and we'll use that to construct Verlinde's ideas. But if the math isn't your cup of tea, relax. I'll give you everything that you need to follow with normal human words. So, the holographic principle grew out of black hole thermodynamics, from the fact that the information that can fit inside a black hole is proportional to its surface area. That information is hidden from the outside world, so this also gives the black hole an entropy, given by the Bekenstein-Hawking formula. It turns out that the same information limit applies to all of space, so that it's in principle possible to encode the contents of a universe on its boundary. In fact, according to the holographic principle, the particles and fields and gravity and laws of physics that govern our universe also play out in lockstep on its infinitely distant but infinitely compacted boundary. On that lower dimensional gravity-free boundary, a very different set of laws encode everything that happens on the interior. The boundary encodes what we call the bulk, and perhaps vice versa. The only concrete mechanism for this that's currently known is Juan Maldacena's ADS-CFT correspondence, which unfortunately doesn't quite apply to our universe. Still, it's a strong lead that there is a version which does. In ADS-CFT, the interior space, the bulk, contains a string theory, and gravity emerges within that string theory. But we don't need string theory.
To be honest, sometimes with, I think, some of the science stuff and even the challenge of a lot of scientists, I think becomes imagination, because in a lot of ways, while they're explaining rules that they know to be true and that they found to be true quite literally, I think there's just so much knowledge that these guys are taking in that there isn't always that much time for true understanding. But I think through discussion and different social things, I think that's where sometimes scientists will be able to get breakthroughs. It's always like, oh, Einstein wrote a letter to this guy. I think that helps because it's like, okay, there's the math, which is literal. There's the physics of it, which is literal. And then the imagination is needed to bridge where it's wrong sometimes.
Theory to see how gravity might be a natural prediction of the holographic principle. Last episode, I showed you a scheme by which this extra dimension can be encoded in the scale of structures on the boundary.
I think I understand a little bit of what he's saying. We'll see when he gets there, but I think he's trying to say that so entropy, which I'm gonna let him explain it when we get to it because apparently, well, so as far as I understand, entropy is the increase of less organization. And I don't even know if organization is the right word, but it's the flow of time in the sense that um, my actual hypothesis is this. I'll say this because I heard one definition on entropy, and it's like an explanation of how microscopic um, systems affect the macroscopic. So it's like all this stuff's going on, right? What's going on though, and why they didn't say subatomic, they said microscopic. So in my hypothesis, the entropy is actually the fourth dimension, and that actually exists on the scale of the atom itself. And so what we see as entropy is because things are not staying still, right? Things are actually moving super duper fast at microscopic scales, but we don't see that. Why? Because we see the sum of it, So it's like we're shocked, right, when something decays or something like that. We're like, oh, how come that thing didn't just stay together forever? Well, it's atoms. While we're chilling over here, the electrons are flying around. The atoms are running and they're bumping into each other, smacking this dude, that dude, smacking this dude, this atom's coming in, smacking that dude. All atoms, all the dudes are atoms. Um, and so the macro effect of that is that things are pushing against each other. They're going to spread out. They're going to um, fall apart. And because of that, they're not going to do the opposite. All this smacking together, they're not going to smack together and build the Eiffel Tower out of nothing. Well, maybe one in a trillion times, but maybe less than that. But in general, it's not going to happen. So he's saying that if the holographic principle, whatever that is, some sort of macro pseudo field, anyway, is at the boundary of our universe, then the entropy of that's what I think he's saying, that the entropy of that might be what we call gravity. So let's see if I'm even kind of right.
With larger structures on the boundary manifesting as structures closer to the centre of the bulk. Today, we're going to explore one idea for how gravity can also emerge within that space as a statistical side effect of the interplay of whatever it is that's happening out there on the boundary. This is the entropic gravity of Eric Verlinde. Now, entropic gravity is by no means broadly accepted, but it is taken seriously by reasonable physicists. After all, there is a fascinating and still mysterious connection between gravity and entropy, as Bekenstein and Hawking discovered. And there's a fascinating neatness to Verlinde's idea that seems like it's telling us something, even if it isn't the whole picture, and maybe even if it's wrong. To understand how gravity might arise entropically, let's think about a less out there system. We'll use the same thought experiment that Verlinde uses in his entropic gravity paper. Imagine a long molecule that is free to move and fold in any direction. We place it in a box of constant temperature with one end fixed to the wall of the box. If we ignore any possible external forces acting on the molecule, we might expect it to just curl up. This is because of all the ways the molecule could move, it's far more likely to end up in a coiled configuration than remain straight. This is one way to think about entropy. The molecule will almost always take a more probable, higher entropy configuration of being curled up because there are way more configurations, or what we call microstates, in which the molecule is curled compared to it being straight. Being in one of the many random coiled states is a higher entropy configuration than the very few straight states. If we straighten the molecule, we have to exert a force and expend some energy to do so. If we let go, it'll curl up again because there's an effective force pulling it back. I should add that there's nothing magical going on here. The molecule shares its temperature with the air in the box, the atoms have randomly oriented vibrations and are being randomly smacked by air molecules, and these will pull and push the molecule towards random configurations, which are overwhelmingly the coiled ones. There's a simple relationship between the force required to pull the molecule or the entropic force that the molecule exerts on you. This is really saying that the amount of energy, the force times the distance pulled, is equal to the temperature of the system times the change in entropy after that little motion happens. Or that the force is equal to the temperature times the entropy gradient. And we call this an entropic force. It's exactly what you experience when you pull on an elastic band. In fact, any time you have the movement of matter in the service of increasing entropy, there's an entropic force. For example, if you force all the air in a room into a box and then release it, it'll rush to fill the room and generate an enormous entropic force in doing so. The proposal of Eric Verlinde is that gravity is also an entropic force. At first glance, that seems odd. Gravity is a property of spacetime itself. Even empty spacetime, so what exactly is pushing or pulling in empty space? Verlinde constructs his argument in the context of a holographic universe, in which at least one dimension of space is also emergent. He argues that the entropy of the stuff on the holographic boundary must increase, and that rising entropy manifests as gravity in the interior. To build up this idea, we're going to need to keep in mind.
So, I mean, there's a lot of things going on there from my perspective. And uh, one, the holographic principle itself is fascinating. But I suppose what he's saying is that you can describe, I don't see how that makes gravity emergent, but you can describe gravity as a linear sort of, I don't know if that's correct, um, mm, entropy in a certain type of way, or maybe a quantum entropy, which kind of makes sense. So, interestingly enough, I've started in my own hypothesis to believe that holograms, or even the concept of holograms, are also somewhat related to the 10th dimension, and maybe all fields in general. It's like, what are fields? Uh, it's fascinating. And then he's saying, yeah, I mean, it's a very fascinating perspective that I think is cool. I think it's big. I think, in my hypothesis, that it's the beginning to understanding that there are multiple dimensions. He's saying in this one you would consider even one of the spatial dimensions to be emergent. So, because what the hologram is that they're talking about, the holographic principle, is that the hologram is us, but the what's real is that there's a shell outside of the a 2D sheet shell, kind of like that's around the black hole, which, okay, I don't know if that helps at all, but that's around the entire universe, and everything's actually happening on that shell, and it creates the holograms that are us, which is fine. I think the problem with that a little bit is how human beings think about holograms as just like fake things that we make, but I don't really think that's exactly what they're saying. I think they're really getting into what are fields and what is this fascinating enough, I think the fields themselves, I think, are created by a force, which science, of course, doesn't agree with that at all. But let's keep watching.
Mind dual pictures. Something is happening on the boundary and something is happening in the bulk, and they encode the same thing, even if they sit very differently in our mental imagery. We'll flip between them as convenient and even merge them slightly. But remember that these are two distinct ways of describing the same system. Okay, so somewhere in the bulk of a holographic universe we have a star with some mass. Let's see if we can figure out the gravitational force produced by the star without ever using any theory of gravity, just by visiting the boundary. To derive such a law, we want to know how much gravitational force is felt at different distances. So let's imagine a series of spherical surfaces around the star. If the star is massive and compact enough, then one of these surfaces would be an event horizon and we'd actually have a black hole. Then the entropy of that surface would be the Bekenstein-Hawking entropy. Basically, it would represent the amount of information of everything that previously fell through that surface. But even if this surface isn't an event horizon, we can give it an entropy. It's also the entropy of everything interior to that surface. But that makes the most sense if we zip out to the boundary. If this is a holographic universe, then the particles on this surface map to the boundary. In fact, the particles on surfaces of all sizes map to the same boundary and play out together, overlapping in that lower dimensional space. We want the entropy of this one surface with respect to someone outside that surface. That translates to how much information is hidden within that surface. Let's start with the holographic boundary from which our bulk universe emerges. Imagine that it emerges from the outside in. Now that's not really the case, but it helps us represent this visually. We're going to partially emerge our universe down to this one surface, so we can depict a special subset of the boundary as actually lying on this surface in the bulk. This is the part of the boundary that corresponds to everything below this surface. So from now on, when I say boundary, I mean the component of the holographic boundary corresponding to the region of the bulk enclosed by this surface. Okay, hold on for just a little bit of math. We know that this surface contains a mass, so we can say that it also contains energy by Einstein's E equals mc squared. That's the energy of the interior, but it also has to be the energy of the corresponding holographic boundary. We
Hmm.
can also give that boundary a temperature, assuming the stuff on the boundary is in thermal equilibrium so that that energy is evenly spread over all possible states. And that n thing is just the number of possible states on the boundary and the total number of arrangements of particles inside the volume that would give you the particular values of energy, mass, and temperature. But that also corresponds to the amount of hidden information within the surface, its entropy. We know the maximum value for this. It's the Bekenstein-Hawking entropy. So the number of Planck length squares over that surface. For our surface, let's just assume that the entropy and n are still proportional to the surface area, but presumably smaller than for a black hole. Okay, one more step. We want the gravitational force, so we need another particle to feel that force. Let's add a tiny mass and move it close to the surface from the above emerged part of space. When that happens, the entropy of the boundary increases because the information from that object is lost to the external region. The boundary gains the same amount of entropy as dropping something into a black hole event horizon. This equation is just saying that the surface gains minimal entropy, equivalent roughly to a bit when the particle merges with the surface, which we define as it getting within its own quantum wavelength, in this case the Compton wavelength of the surface. But just like we saw with the coiling molecule, this tiny increase in entropy should have a corresponding entropic force. Whatever crazy interactions are happening out there on the boundary, they are statistically inclined to bring our particle closer to this surface because that motion increases entropy. If we bring everything together, the delta S over delta X from dropping a particle through the horizon, and the temperature from the overall entropy of the surface, all the h bars and the c's and the kb's cancel out, and we replace the area of the sphere with 4 times pi times its radius squared, and we see that the algebra shakes down to Newton's universal law of gravitation within some constant. And if that constant is 1, because we got our surface entropy formula right, then we have Newton's exact equation. We just derived Newtonian gravity with arguments that are entirely thermodynamic. This is basically saying that if objects in the bulk move in such a way as to maximize entropy on the boundary, then that motion means falling towards other masses in the bulk. Remember that.
Okay. So he's saying the way of describing gravity is by looking at three-dimensional things two-dimensionally. You know what's fascinating about that? And we'll enjoy this, but I will. Part of the hypothesis that I've been working on is that dimensions work in pairs. So first and second dimension are in a pair. Third and fourth dimension are in a pair. Fourth and fifth dimension would be in a pair. And the way that the pairs relate to each other are, via that first emerging. I'm not going to say emergent because it's not really emergent. Z-axis, right? So if you take an XY axis, that is a good representation of any two-dimensional pairs. XY axis. Now, if you want to draw a Z-axis, how would you usually do that? You would draw it as a 45-degree angle, but also realizing that it's non-collapsible. It's not on the plane of the XY axis. It is separate in whatever way you want to call it. And so, what did he just say? Sorry. Go back a second.
Means falling towards other masses in the bulk.
Right. So if you were to take away the third dimension, because he's saying to collapse, or to consider one of the three dimensions of space emergent. So there's really only two dimensions, which is, I guess, how the holographic principle works. Then you find that things naturally attempt to collapse. And so since that happens in the holographic way, it's a type of, and it's very fascinating. I think part of the reasons, my hypothesis says that part of the reasons we can't discover quantum gravity is because we don't really understand that whole relationship of the fifth and sixth dimension. I think quantum is the sixth dimension, by the way, I should say that. And so that release, because they're in relational pairs, it's like kind of impossible to separate them. And to see them. And since we're used to dealing really with only sub-gravity forces in math and things like that, to a degree anyway, it's hard to see, to be able to find that relationship between the fifth and sixth relationship, because really that's not what they're looking for. So that's interesting. I think that kind of relates that idea to me of perhaps just that it makes sense, and it's a good approach to finally figuring out a good way to talk about gravity.
Remember that Hawking and Bekenstein used gravitational theory and quantum mechanics to get black hole thermodynamics. But entropic gravity turns this on its head. It starts with thermodynamics and finds that gravity just falls out. But let's not get ahead of ourselves. Firstly, this is just Newtonian gravity. Can entropic gravity reproduce Einstein's general relativity? Well, in the 2010 paper, Verlinde argues that yes, it can, although the derivation is a bit much for this episode. In 2016, he also published another paper that argued that dark matter can be explained by this idea and that it's connected to dark energy, although this requires some extra assumptions. And speaking of...
If you know me, I've been saying that both dark matter and dark energy are the same thing, just in different conditions. Dark energy is dark matter outside of the universe. But I like that as well. I also think that both of those are related to the quantum in the sixth dimension. Very cool.
assumptions, the validity of this whole idea rests on the validity of the founding assumptions. Not least of those is the requirement of a holographic dual to the gravitational universe. And unless we can find a version of ADS-CFT that works for our universe, this feels like a big if. The debate over entropically emergent gravity is real, and is taken very seriously by serious physicists. That means it's worth doing another episode to pick this apart. But in the meantime, this has been pretty hard work, so let's just...
Loved this episode. Really great explanations, PBS. Shout out to you guys. It's very fascinating. I think the core of what I leave away with it, what I'd like to look into a little bit more, is that concept I was telling you about of really figuring out, okay, if gravity's the x-axis and quantum is the y-axis, what type of quantum gravity should we be looking for? That's the question I want to ask. And one day someone will get the answer and we'll get to watch their video and react to it. Or maybe I'll get the answer, or maybe you will. In the meantime, go ahead and like and subscribe. I appreciate you guys so much. Definitely go watch PBS Spacetime. And hopefully we'll get to talk again soon. Thank you guys so much. Remember, subscribe. It's free. It's free for you. And it's low entropy for me. See you later.